Hi everyone, and you're very welcome to today's Saturday session, where our subject for today is Junior Cycle Science, and the topic we're going to be looking at is the atom and then predicting the ratios of atoms in compounds. So before we get into the actual structure of the atom, we're going to look at historically what people believe the atom actually looked like. And around 2000 years ago, ancient Greeks believed that everything was made of 4 elements. So you've probably heard of these before. We had earth, air, fire, and water. Okay, and that's represented in the image we can see over on the right hand side. So they believed that everything was made up of those and combinations of those. But around 200 years ago, John Dalton developed another idea. He suggested everything was made up of these tiny particles called atoms. And he also suggested that these atoms could be joined together to form new substances. So the ancient Greeks, I suppose, weren't too far wrong in the idea that combinations of things formed new substances, but they completely missed the idea of the tiny particles called atoms. That was John Dalton. So these atoms joined together, they would form our new substances. And that's what we're going to be investigating later today. We're going to look at the structure of the atom and how these can be joined then to form new substances. So what is an atom? An atom is a tiny particle. We cannot see them with a light microscope, so they're the microscopes that you'll have in your school laboratory. We need an electron microscope to be able to see them, so it's a more powerful microscope. An atom is the smallest part of an element that also has the same properties as that element. So all of our elements are listed on the periodic table. Okay, and all of the elements that are on that periodic table are composed of atoms. Okay, so for example, the element oxygen is composed of oxygen atoms. Fluorine is composed of fluorine atoms. Chlorine is composed of chlorine atoms. Okay, these atoms, they're the smallest part of that element, but they have all of the same properties as that element. So all of the oxygen atoms in the oxygen element, they have the same properties. All of the carbon atoms have the same properties as the element carbon, and so on. Okay, so for example there, oxygen is made up of oxygen atoms. Now the structure of the atom. Atoms are made up of 3 subatomic particles. Okay, the 3 particles we have protons, we have neutrons, and we have electrons. We're going to see exactly where they're housed in a couple of minutes and charges associated with those. But if we have a look at the simplified diagram over here, we can see in here in the center, in our nucleus, that's where the protons and the neutrons are located. The electrons exist on these rings or shells or clouds that orbit the nucleus. So protons and neutrons in the nucleus, electrons on the outside. So again, our protons and neutrons in here in the center, they're housed in the nucleus. And we can see here that protons have a positive charge. Okay, so P for proton, P for positive, they're found in the nucleus. Along with the protons, the neutrons are also found in the nucleus. So N for neutron, N for neutral. Neutrons have a neutral charge. They're neither positive nor negative. Okay, they're also found in the nucleus. And electrons have a negative charge, and they're located in the electron cloud. Sometimes they're called rings or shells or orbits. Okay, there's lots of different names for where they exist. So it's these rings or shells or clouds or orbits that go around the nucleus. Okay, and we can see the charge there for the electrons as well. We can see that they're negative. That's the protons. And then the one with no charge highlighted is the neutrons. Okay, so just a summary so far, we're also going to look at the relative mass as well now in a minute. The electrons have a charge, negative charge, that's why it's a -1. They're outside the nucleus on the clouds or the shells or the orbits. The protons, they have a positive charge, that's why there's a +1 there. They're located in the nucleus. And the neutrons, they have a neutral charge, neither positive nor negative, and they're also located in the nucleus. Now for the relative mass, protons and neutrons, we say, are 1 atomic mass unit, so 1 AMU. Okay, so that's the protons and the neutrons. The electrons have a relative mass that's much, much smaller than that. To be precise, it's 1/1840th. Okay, so you would need 1,840 electrons to have the same atomic mass as either a proton or a neutron. Okay, so it's important to know those as well about the relative masses. So 1 AMU, 1 AMU, and 1/1840 AMU, so atomic mass unit. We're now going to look at the periodic table and the elements that exist on the periodic table and how the atoms of individual elements can differ from each other. So for example, the oxygen atoms are going to be different from the carbon atoms. They're going to be different again from the nitrogen atoms. And we're going to see what those structures actually look like. Every element on the periodic table has two numbers on it. We have a smaller number and we have a larger number. And more often than not, that's going to be rounded to the nearest whole number. So for oxygen, that's going to be 16. The top number is known as the atomic number, and the atomic number details the amount of protons and actually electrons that a particular element has, okay? Because the protons and the electrons are always going to be equal to each other. So this atomic number up here, the smaller number, the 8, is telling me that oxygen has 8 protons. But because it has 8 protons, it's actually telling me that there's also 8 electrons there as well. Now the bottom number is called the mass number. So that's 16 in this case. And this tells us the total number of protons and neutrons added together. So 16 in this case is equal to the protons plus the neutrons. But we already know that we have 8 protons. So what number does n have to be to add to 8 to give us 16? In this particular case, n would also be 8. Okay, that's just complete coincidence that the number of neutrons, protons and electrons are all 8. That's not always going to be the case, but in the case of oxygen it is. Okay, so the Bohr structure of atoms then is the next thing we're going to look at, and then we're going to combine the knowledge from both to start to produce these structures. So Danish scientist Niels Bohr came up with the idea of electron shells to explain atomic structure. So those were the ones that the electrons existed on. He proposed that the first shell holds a maximum of 2 electrons, and we can see that here. That's the first shell there, and we can see that there was actually 2 electrons on that first shell. So a maximum of 2 on that first shell. The second, third, fourth, fifth, sixth, and so on can all hold a maximum of 8 electrons. Okay, you cannot move on to the next shell until the current shell is full. So for example, we have a full inner shell here. That first one can only hold 2. That's full. That's why we moved on to the second one. Okay, currently we have 1, 2, 3, 4. If I had any more electrons to draw as part of this Bohr structure of carbon, I couldn't start to put them on the third shell yet because this second one is not full. It needs 8. The second, third, fourth, fifth, sixth, and so on all need 8. It only has 4. It's not full just yet. Okay, and we're going to see where these structures came from now in the next couple of minutes. So the example we've already seen was oxygen. The atomic number was 8, so this was this particular number down here. That tells us the number of protons and by extension tells us the number of electrons. They're both equal to 8. The mass number was 16, that was this number down here. That tells us the protons plus neutrons added together had to be 16, but if the protons are 8, that means the neutrons also have to be 8 because the total has to be 16. Okay, so we're going to see what this actually looks like now when we draw it. Alright, so here we go. Just to remember, we had 8 protons, 8 neutrons, and 8 electrons. That's what we figured out from our calculations. Let's have a look at the nucleus first of all. We're going to split that nucleus in here, and I'm just going to do 8p and 8n. Okay, because in the nucleus I have 8 protons and 8 neutrons. So they're accounted for over here. I also need 8 electrons. Now on that first shell, I'm only allowed to have 2. So there's the first electron, there's the second electron. Okay, you don't have to number them, I'm just showing where they come from. We've used 2, that shell is full. I have to move to the second shell for any subsequent ones I have until that shell is full, and then I can move to the third. Now if I've already used 2 electrons, I still have 6 to go to get to 8. So there's the third one, the fourth, the fifth, the sixth, the seventh, and the 8. So that's the 8 electrons of oxygen. There's no more need to be included. Okay, I do have room, if this was another element, to include an extra 2 electrons on the outside shell, because that one there currently isn't full. But for this one, we don't have to worry about that, and all the electrons have been accounted for. Now, instead of numbering them, generally, if you were to draw your Bohr structure, we would label the electrons as E-, okay, because they're electrons and they have a negative charge. So beside each electron, I'm just going to do a little E minus to show that they're electrons and they have a negative charge. And that there is your Bohr structure of oxygen. Okay, we're now going to try and do the same thing for nitrogen. So we have our atomic number up here, we have our mass number down there, which is 14. So up here, our atomic number tells us that the number of protons is equal to 7, but that's also telling us that the number of electrons is equal to 7. Down here, our mass number tells us that the number of protons and the number of neutrons has to be equal to 14. Now, we don't know the number of neutrons just yet, but we do know when we add that to 7, which is the number of protons, we have to get 14. So the number of neutrons is also equal to 7. So again, that's just coincidence that we get all of the same numbers for each one. That's not always going to be the case. So let's have a look at the Bohr structure. So in our nucleus, just remember, neutrons were 7, protons were 7, and electrons were 7. So in the nucleus, we have 7 protons and 7 neutrons. Okay, they're accounted for. We now need electrons. So on that first shell, we're allowed to have 2. So there's 1 electron, there's the second electron. Okay, we've used 2, we still need 5 more. We're allowed to have up to 8 on every shell after this. We actually don't have to fill this shell because we only need 5. Just make sure and space them out as well because it does make it easier to read. So there's 4 and there's 5. Let's just double check. 1, 2, 3, 4, 5, 6, 7. Okay, that's all 7 electrons which we needed to account for. So that there is the Bohr structure of nitrogen. Same one here for carbon. So we have our atomic number. So that tells us that the number of protons is 6 in this case. Number of protons is 6. The number of electrons is 6. And this number down here of 12 tells us that the number of neutrons plus the number of protons has to be equal to 12. Now the number of neutrons we don't know yet, but we do know when we add that to 6, we have to get 12. So what number do you add to 6 to get 12? Well, that tells us the number of neutrons are also 6. So again, just coincidence that we're getting the same answers for each one, not always going to be the case. So we'll have a look at our Bohr structure here. So neutrons was 6, protons was 6, and electrons was 6. So in the nucleus, we have 6 protons, 6 neutrons. On the first shell, we have 2 electrons, and we need all 2 because we have a total of 6 to include. And then on the second shell, to get us to a total of 6, we only need 4. So it's not a full shell at all. There is room for more, but we don't need it for carbon, and there's all 6 accounted for. Okay, so that's the Bohr structure of carbon. Now, one extra thing I'm going to include in here is our electronic configuration. And this just details the number of electrons that are on each shell. So for carbon, the electronic configuration of carbon would be 2, 4, because we have 2 on the first shell, 4 on the second shell. Okay, if we think back to oxygen, where we had 2 and 6, it would be 2, 6. So that's just something to keep an eye on as well. If you ever get the electronic configuration like this, it's actually telling you straight away the number of electrons to draw on each shell. So this will be the last one we attempt now. So this is potassium. So this atomic number up here tells us the number of protons is 19. Also tells us that the number of electrons is 19. And this number down here tells us that the number of neutrons plus the number of protons has to be equal to 39. We don't know the number of neutrons yet, but we do know when we add that to 19, which is the number of protons from up above, we have to get 39. So what do you add to 19 to get 39? We add 20. So the number of neutrons is 20. So in this case, we actually don't end up with the same number for all 3. So protons was 19. neutrons was 20, and electrons was also 19. So in the nucleus, we have our protons and neutrons. 19 protons, 20 neutrons, they're accounted for. And now we need 19 electrons. So on that first shell, we're allowed 2. Still have 17 more to go. So we open up our second shell. We can actually include all 8 this time, because even when we include all 8, we're still not going to be at 17. We'll only be at 10. So that's a total of 10 electrons so far. We need 9 more. So we'll open up our third shell here. We can actually fill this one up as well, because this is only going to bring us as far as 18. We need to get to 19. Okay, so that's 18 electrons, and we need one final shell now. And this is going to be for our 19th electron. Okay, so now we have 19. So the electronic configuration for potassium, we have 2 on the first shell, 8 on the second, 8 on the second, and 1 on the last, giving us a total of 19. So all electrons are accounted for. Okay, so we've kind of already looked at the periodic table to an extent when we were looking at the individual elements a couple of minutes ago for the Bohr structures, but we're just going to look at it in more detail now. So each element has its own symbol, and we've already seen that. So oxygen was O, carbon was C, potassium was K, nitrogen was N, and so on. So we've only dealt with ones that had one singular letter, and it was always a capital letter. So their names are either based on the English name, the Latin name, or possibly the scientist who discovered it or where it was discovered. Okay, if there is one letter, it's always a capital, as is the case up here. If there's 2 letters, the second one is always a small letter. So an example of that would be lithium, which is capital L, small I. Okay, so that's just correct notation for chemical symbols. All of the elements can be found on the periodic table, and you can see that it is arranged in a coherent manner. So you can see the atomic numbers here is increasing as we go down. Okay, so we're going to look at that in more detail now, and how we can combine different elements to form compounds, form new substances, which is exactly what we were talking about at the start when we were discussing the atom. Okay, so we're going to examine the periodic table now and talk about these 2 terms called groups and periods. Okay, there are 8 groups in the periodic table. The first 2 groups are along the left-hand side, and the next 6 are over along the right-hand side. So you can see that they are color-coded there. Some of them do have names, which we'll come to in a couple of minutes as well. Okay, so they're the groups. The groups are the vertical columns. Okay, so they're going down. That's group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. The periods are the horizontal rows, so they're the lines going across. Okay, so period 1, period 2, period 3, period 4, period 5, period 6, and so on. So if we were to look at that, that would be period 1, 2, 3, 4, 5, 6, 7, and so on. So we start on period 1. What these numbers here tell us is the number of shells. So anything in period 1 only has 1 shell. Okay, so that means they have a maximum of 2 electrons because they don't need to move on to the second shell. Anything in the second period has a maximum of 10 electrons. Okay, they're either going to have between 3 and 10. They do need to move on to the second shell, so they definitely have more than 2, but they don't need to move on to the third, so they have less than 10. Anything in period 3 is going to need 3 shells. Anything in period 4 is going to need 4 shells. Period 5 is going to need 5 shells, and so on. Okay, that's the pattern there. The group number tells us the number of electrons on the outside shell. So that's actually really, really handy for us. If I was to pick an element at random, let's say this one over here, okay, what is this telling us? Well, this is in period 2, okay, so it needs to have 2 shells. There's our 2 shells. But the group number is also telling us the number of electrons on the outside shell. Okay, so it has 4 on the outside shell. Now remember, you can't move on to the second shell unless the first one is full. So the first one is full, the second one has 4. Okay, so we can actually see that that has a total of 6 electrons in total. If we were to pick another random one over here, let's say for example this one here, it needs to have 3 rings, okay, because it's in period 3. So I'll draw my 3 rings. but it's also telling me that on the outside one I have 5 electrons. Now remember, you can't move on to the next ones unless the previous ones are full. So the first 2 are full, and there's 5 on the outside one. Okay, so it's a really, really handy way of telling us the number of rings and the number of electrons that are on the outside shells. So I did mention how there was some names for some particular groups. This is a couple of them here. So group 1, this entire group on the left hand side, they're known as the alkali metals, and it's really important that we know that. So that's the alkali metals, AlKali. Group 2, similar in some regards, but it's the alkaline earth metals. So AlKaline, so slightly different variation of that. That's the alkaline earth metals. That's all of column 2. We're now actually going to skip over to column 7 and 8. You don't need to know 3 to 6. Group 7 is known as the halogens or the halogens. Okay, that's all of group 7 down here. And group 8 are known as the noble gases. And what's really important about the noble gases, remember the group number, in this case group 8, tells us the number of electrons on the outside shell. Okay, they're noble because if they have 8 on its outside shell, that means they're full. They've full outer shells. Okay, so everything in group 8 has a full outer shell. So they're not very reactive. That's all they want, is to have a full outer shell, so they're quite happy just existing. So we're going to have a look at an exam question or two here now. So an atom of element X is shown in the diagram. Name one subatomic particle found in the nucleus. So that's our keyword there. It has to be found in the nucleus. That's actually eliminating electrons for us. So one of the subatomic particles will be protons. Okay, we're going to be really careful to only list one of them. We're not going to list 2, but the other one would be neutrons. Part of the question then, answer the following question by putting a tick in the correct box. The charge on the electron is it positive, is it negative, or is it neutral? We know that that's negative because when we're depicting electrons, we do E minus. The minus sign there is depicting for us that it's supposed to have a negative charge. Another question here, an atom of sodium has an atomic number of 11 and a mass number of 23. So remember, the atomic number tells us the number of protons, and it actually also tells us the number of electrons because they're going to be the same. The mass number is the total of the protons plus the number of neutrons added together. I'll just write that down below just in case I run out of room. So it's the protons plus the number of neutrons. So let's use this information now. How many protons does this atom contain? Well, if the atomic number is 11, we know the number of protons is going to be 11. How many neutrons does this contain? Well, the mass number is the one that we need for this. This number here, 23, is the number of protons plus the number of neutrons added together. So if we already have 11, what do we have to add to get 23? Okay, so the number of neutrons in this case would have to be 12. Complete the diagram below, drawing all the electrons in the Bohr structure for the sodium atom. The 2 electrons on the first shell have already been drawn for you. Now we know, because of the atomic number being 11, we have to have 11 protons and 11 electrons. Okay, we also have 11 protons down here plus the 12 neutrons to give us the total of 23. So we don't actually have to label the nucleus here in this case, it's just the electrons that we're worried about. We already have 2. You can draw X's or you can draw the dots with the E minuses, it's up to you. But we need to fill that second shell. We're allowed to have 8. So that's the 8, bringing me to a total of 10, because we had 8 plus 2 is 10, but we need 1 more to get us to 11. So that there is the atomic structure of sodium. Name the group of the periodic table to which sodium belongs. Now remember, this has 1 electron on its outer shell, so that means it's in group 1. If it had 2 electrons on its outer shell, it would be in group 2. If it had 3 electrons on its outer shell, it would be in group 3. But it only has 1, so it's in group 1. And the name of group 1 are the alkali metals. Okay, so that was another exam question then based on the Bohr structure. Now, before we move on and start to have a look at how atoms can be joined together to form new substances, we're just going to do a quick pit stop check of how we're getting on. So atoms are made up of 3 different subatomic particles. We have our protons. They're found in the nucleus and they have a positive charge. We have our neutrons, which are also found in the nucleus, and they're neutral. They're neither positive or negative. And then we have our electrons. They're found orbiting the nucleus, so in clouds, shells, rings, whatever you want to call it, lots of different names for those, and they have a negative charge. So electrons are going to stay in the rings or shells around the nucleus. The first shell, remember, can only hold 2. Every shell after that can hold 8. You cannot move on to the next one until the previous one is full. Okay, so 2 in the first one, 8 on every subsequent one after that. Okay, we're now going to have a look at chemical bonds, and you've definitely heard of some of these before. So a compound forms when 2 or more elements chemically combined. Okay, we're only going to examine when 2 elements chemically combine, but you can have 3, you can have 4, you can have 5, you can have any number, but we're just going to examine the cases when 2 elements chemically combined. Now, a famous example, which you might have heard of before, is H2O. Now, what does this actually mean for us? Well, if we have a look over here, here is a chemical symbol, here is a chemical symbol. Remember when we were talking about the periodic table a couple of minutes ago, when you're listing an element, if it just has one letter, it's a capital. That's why H gets a capital and O gets a capital. They're 2 separate elements coming together. This subscript here, okay, the little smaller letter 2 or number 2, that's telling us that we have 2 hydrogens, H2, okay? This O, there's no number actually wrote there. That just means we have 1. This is actually the chemical formula for water, okay? So within water, we have 2 hydrogens and we have 1 oxygen. Now, how does this actually come around? Well, that's what we're going to be looking at in the next couple of minutes, using the periodic table to predict if you were given 2 random elements, if they were to combine, how many of each would you need in order for them to be able to chemically combine, and what would the chemical formula end up being, just like water is H2O. Now, in order to be able to do this, we need to introduce ourselves to another key word, and this key word here is valency, but you've actually already dealt with this already. So in order to be able to predict how many of each atom there will be in a bond, so why did we have 2 hydrogens and 1 oxygen in H2O, we need to know about valency. So valency is the maximum number of electrons an atom of an element will either give, take, or share with any other atom. Okay, so it's kind of counterintuitive when we talk about it, but I'll talk you through it now. Why is this +1? Why is this 2? And so on. Well, if we have a look at hydrogen, hydrogen is in the first group and it's also in the first row. Okay, so if we were to draw hydrogen, that's what it would be there. Lithium, sodium, potassium, and so on, they would all be very, very similar. On their outer shell, they're only going to have 1 electron. Okay, so think about this. If they were trying to get a full shell, is it easier for every element in group 1 to either get an extra, for lithium and so on anyway, get an extra 7 electrons to fill that outer shell, or is it easier for them to lose that 1 electron that's on their outer shell in order to get the full outer shell? Okay, it's a lot easier to lose 1 than it is to gain 7. Okay, that's why they have a +1, because if they lose that electron, they're losing a negative charge. They're only losing 1 of them, so that's why it gets a +1. They're losing a negative charge, so they're actually somewhat becoming more positive, if that makes sense. In group 2, they all have 2 electrons on its outer shell. So is it easier for them to get an extra 6 to fill it to 8, or to lose 2? It's easier to lose 2. Okay, so they're losing 2 negative charges. That's why it's a +2. It's similar here for group 3. It's easier for them to lose 3. For this middle one here, they actually have 4, so it's somewhat the same. They can either gain 4 or lose 4. It doesn't make much of a difference. For this group here, they have 5 on their outer shell, so it's easier for them to gain 3, so get 3 more negative charges. That's why we have a -3. We're getting more negative charges. Group 6, we need to get 2 more negative charges. Group 7, we need to get 1 more negative charge. And group 8 is full. We're not going to worry about them. Okay, so that information there, these numbers on the 8 groups which we have in the periodic table are hugely important for us. Don't worry about the plus negative charges. Just know 1, 2, 3, 4, 3, 2, 1, 0. Okay, so starting on the left, go up to 4 and then back down to 0. Those numbers are crucial for predicting the number of atoms and compounds. Okay, we're now going to look at how we can use this valency information to predict the following. So what chemical formula do we have when we bind magnesium and chlorine together? So just one thing to keep an eye on here. These 4 little subheadings along the left hand side are never going to change when we're doing these, so it's really important to know them. We write down our symbols, we write down the valency, we switch the numbers, and then we form our formula. They're crucial for us. So the element symbols, magnesium is Mg, we can see that over here. Chlorine is Cl, which we can see over here. So I said earlier on, you can ignore the positives and the negatives, that's all fine. But the valency for magnesium, look at the number up here, it's 2. That's why it's crucial to know these numbers, 1, 2, 3, 4, 3, 2, 1, 0. Magnesium is 2. Chlorine over here is 1. Okay, so 2 and 1. We switch the numbers, okay? That means in our chemical formula, we're going to have 1 magnesium and 2 chlorines. So we get MgCl and then a small 2 because we have 2 chlorines. Okay, that's the same for every single one that we do. So we'll have a look at another. So what happens here when we combine hydrogen and oxygen? Now we know this is actually going to be water. We'll get to this in a second. So our element symbols, hydrogen is H, oxygen is O. Okay, the valency. Hydrogen is 1. Oxygen over here is 2. Let's switch the numbers. So the 2 goes over here, the 1 goes over here. That means we have 2 hydrogens and we have 1 oxygen. You don't have to write the 1, you can actually just leave that as just the O, okay? So H2O, when you combine hydrogen and oxygen, that's what we end up with. So another example here, we have carbon and hydrogen. So carbon is C, hydrogen is H. If we have a look at the valency, carbon is 4, hydrogen is 1. We're going to switch the numbers. And we get 1C, so you can just write C, and then we're going to have 4 H's. And that there is actually methane. So if you ever see CH4, that's methane gas. Okay, so it's the exact same steps the whole way throughout. Write down the element symbols, write down the valency, switch the numbers, and then you're easily able to form the chemical formula then from that. So we have one more example here. This is magnesium and oxygen. So the element symbols, we have Mg for magnesium. Make sure the second letter there is a small letter. We have O for oxygen. The valency, magnesium here is 2. Oxygen is also 2. We'll switch the numbers. So we get 2 and 2. So we'd end up with Mg2O2. Now because those numbers are the same, we can actually simplify that to MgO. Magnesium oxide is always given as MgO. You're not wrong if you put down Mg2O2, but the simplified version is MgO. Okay, so the exact same process there again. Okay, so we'll have a quick look at this one here. Complete the table below using the periodic table of elements to predict the ratio of atoms and the chemical formula for each of the following compounds listed. You should refer to page 79 of the Formula and Tables book when answering this question. So I have a screen grab here from the Formula and Tables book. I'm just going to number the groups. So 1 and 2 were actually already done. Go the whole way over to the other side where we'll have 8, 7, 6, 5, 4 and 3. Now the valency is the most important thing here. That is a valency of 1, 2, 3, 4, 3, 2, 1 and 0. Really important that we know those valencies. Now we have magnesium and chlorine. So I'm not going to write down the subheadings along the side, but I am going to follow them. The first one is the chemical symbols, so magnesium and chlorine. Then we write down the valency. Magnesium has a valency of 2. Chlorine has a valency of 1. That's it over there. So chlorine has a valency of 1. We switch the numbers. So our chemical formula is going to be MgCl2. Okay, so it's a ratio of 1:2. We have MgCl2. So we'll have a look at the next one here. We have nitrogen and hydrogen. Nitrogen is here. It has a valency of 3. Hydrogen has a valency of 1. Switch the numbers and we get NH3. So it's a ratio of 1:3. Chemical formula is NH3. Okay, so really important there that we know the valency of each one of those, because that's really going to help us when we're answering out that question. And if you follow these steps of the chemical symbol, write down the valency, switch the numbers, form the formula, you'll be having no issues with that. So another question which has appeared on the state exam, we've already seen part of this before, but we'll do it again here. Name one subatomic particle found in the nucleus. So that's either the proton or the neutrons. Make sure only write down one. Answer the following, putting a tick in the correct box. The charge on the electron is negative. That's why we are writing E minuses. Place an X on the periodic table below to indicate the position of element X. Okay, you may use the periodic table on page 79 to help you answer this question. So we could use the periodic table if we wanted to from the previous slide, but if we have a quick look here, we've 1, 2, 3, 4, 5, 6. So we're looking for element number 6. So 1, 2, 3, 4, 5, 6. So that's actually going to be it there. I'm not going to write down the number 6. I'm going to put in the X like they wanted me to. Element X, and we actually know that this is carbon in this case. When you look at the periodic table, that's carbon. So this is what it will look like on the periodic table. Element X forms a compound with hydrogen. Element X is shown in grey. Hydrogen is shown in green. Circle the diagram below which represents the compound formed and justify your answer. Okay, so hydrogen we know is the very first one up here. So that's hydrogen. Let's write in the valencies. 1, 2, 3, 4, 3, 2, 1, 0. Let's follow our steps. So we have carbon, we've hydrogen. Carbon has a valency of 4. We can see that over here. Hydrogen is 1. Swap the numbers and we get CH4. So we're looking for one of the diagrams down here that has 1 carbon and 4 hydrogens. That only has 1 carbon and 2 hydrogens. That has 4, that has 3. So it's actually this one down here. So it says circle the diagram, you've done that, justify your answer. Your justification is actually over here, but you could say something along the lines of carbon has a valency of 4, hydrogen of 1, so 4 hydrogens needed to balance out. So to balance the charge. Okay, so that's an example of an exam question which comes up. That actually came up in the 2022 exam. Okay, so that's all of the content for today. Just before we finish up today, I just want to show you around the ExamRevision website so you can access today's content and even more as well. Now, when you log into the ExamRevision website, you can see not just do we have junior cycle science, we've lots of junior cycle subjects there. We've business, geography, history, home ec, we've Irish, we've maths, and then we have science as well. Each one of them is laid out the exact same way. We've video tutorials, we've quizzes, we've presentations, we've an exam builder, and we've a resource pack there as well, which you can use in class. So if we click into video tutorials, today we were looking at chemical world, and we actually looked at 2 of these. We looked at the structure of the atom, so we can see that there's lots of videos there based on that, and we actually looked at CW5 as well. Now, if you did want to go back over the atomic structure and the electronic configuration, you could just click into the video, watch the video at your own pace. You can change the playback speed to quicker or slower, and you'll be given some related videos there as well to watch. Now, when you have the videos watched, you'll be able to go back and then you'll start to be able to test yourself using the MCQ quizzes, which we have. So if we quickly go back here, we go back into where the videos were, go right down, there's our quiz on the structure of the atom. Okay, so we've 10 questions there which we can use to test your knowledge. Now, once you're comfortable with those, you can actually start to build your own exam as well. So not only are all the past state exam questions on this, all of the past mock exam questions are as well. So you can have a look down through the questions, add whichever ones you want to an exam which you're making, go right back up here to the top, and you can download the questions and download the marking scheme answers as well to make sure that you're in the best position possible going into your final exam. Do keep an eye on our website as well, because we will have loads of information coming of all the revision courses which we're running. These generally run at the midterm break, so February, the Easter holidays, and then May, June in the lead up to the exams as well. Keep an eye on our social medias as well for all of the information, not just about the revision courses, but about upcoming Saturday sessions just like this one as well. So thanks for your time for the Junior Cycle Science one today. Keep an eye out for the upcoming subjects over the next couple of weeks, and I hope to see you for another Junior Cycle Science one in the near future.